let's move on to sex-linked Punnett squares now. Okay, so these are different than the autosomal Punnett squares that we've been doing before. Okay, they're different because now we're looking at sex chromosomes. Okay, and sex chromosomes are different for the genders. Okay, so males have sex chromosomes X and Y. Females have sex chromosomes X and X. Okay, so I'll show you how like it's different when we set up the Punnett squares. Okay, the reason why it'll be different is because the alleles in this case they may be found on the X chromosomes or they may be found on the Y chromosomes. So if you look right here in the males only have one X chromosome. Okay, females have two X chromosomes. So let's say that we're talking about an X-linked trait, meaning that the alleles are found, the genes are found on the X chromosome only. Okay, that means that the females will have two alleles because they have two X chromosomes. Okay, males will only have one allele because they only have one X chromosome. Okay, and then let's say that something is like a trait is Y-linked, meaning that the gene is on the Y chromosome. Okay, males have one Y chromosome, so that means they only have one allele. They can only hold one allele because they only have one Y chromosome. Okay, females have 0 Y chromosomes, so they won't even have that gene or any alleles for that gene. Okay. Okay. So hemophilia is an X-linked trait that is recessive. Okay. The allele, little h, is for hemophilia, and big H is for normal. We're going to cross a female with hemophilia with a normal male. Okay, what are the chances of them having sons? Sorry, that's a typo. With hemophilia. Okay, what about daughters with hemophilia? Okay, so first let's go ahead and do the Punnett square. Okay, so cross a female with hemophilia. The only way that she could have hemophilia is if she is X little h X little h. And then for the male, if he's normal, then he's X big H Y. Okay, so let's start off with the male on the top. He's normal. Because hemophilia is only on the X chromosome and he only has one X chromosome. Okay, we put the H on the X chromosome and then he has a Y. Y doesn't have any hemophilia gene on it. Okay, so we just leave Y alone. Y is just there. Okay, so now we do the mom or the female. So she has hemophilia. Only way that she could have hemophilia, because this is a recessive trait, is if she has two little h alleles on her X chromosomes. Okay, so do the Punnett square. X big H, X little h, X little h, Y. X big H, X little h, Y. Okay. So now, what are the chances of this couple having sons with hemophilia? So here's the thing. This Punnett square is different in the sense that if you look right here in the four squares of the Punnett square, okay, they're different, as in the chromosomes are different. Okay, so you have X, big H, X, little h. Okay, so if you have X and X sex chromosomes, female. Okay, if you have X and Y sex chromosomes, male. So that means the two female genotypes are on the left side, and then two female genotypes for the males on the right side. Okay, so this is actually split. Before, we didn't care about gender for like the regular autosomal Punnett squares, but in this case, because we're talking about sex-linked chromosomes, and there's X chromosome and there's a Y chromosome, now it's different. Okay, so what this means is the question's asking, what are the chances of the sons having hemophilia? So we only look at the son. So basically, this side of the Punnett square only. Okay, because these are the males we're talking about. So in this case, that's hemophilia, that's hemophilia. So 2 out of 2, because we're only looking at males this time. We don't look at the left side because X sex chromosomes are females. Okay, so this is basically saying that if this couple has children, if they have any sons, there's a 100% chance of sons having hemophilia. Okay. For the daughters, this is like the second part of the question says, what about the daughters with hemophilia? So the daughters are on this side, right there. Okay. So those two, X big H, X little h, since hemophilia is recessive, they have to have X little h, X little h for the daughters to have hemophilia. So none of them are like that. So 0% chance. So 0 out of 2, which is like basically 0% chance of daughters having hemophilia. Okay. If you analyze this a little bit further, the reason why it's like this is because the father, who's up here, right? The father's X big H Y. The father does not give any of his X chromosomes and whatever's on that X chromosome to the sons. The father gives the Y chromosome only to the sons. Okay, the sons get the X chromosome from their mother. Okay, it could be this X chromosome with that allele, or it could be this one. Okay, fathers give their X chromosomes to their daughters. The father does not give a Y chromosome to a daughter because then that wouldn't be a daughter, that would be a son. Okay, well, let's try another problem. Squidward's disease is an X-linked trait that is dominant, okay, and is characterized by the fear of flying. The allele big S is for Squidward's disease, and little s is for normal. Cross a normal female with a male with Squidward's disease. What are the chances of sons having Squidward's disease? And then what are the chances of daughters having Squidward's disease? Okay, so let's set up the Punnett square. So cross a normal female and a male with Squidward's disease. So since this is on the X chromosome, right, and this is a dominant trait, that means the male's genotype is, let me erase that for a second. That means, they're X, big S. Nope. Yeah, that's right, dominant. And then they're Y. Okay. And then for the female, the mom, the genotype she has, she's normal. Since this is a dominant trait, Squidward's disease is a dominant trait, any big S allele that the mother has will lead to result in Squidward's disease. So she can't have any of the big S alleles. Okay, so she has to be X little s X little s and then X little s. Okay, so if you do the Punnett square, X big S, X little s, X big S, X little s, X little s y, X little s y. Okay, so if you look at in this case, what are chances of sons having Squidward's disease? So the sons on this side, X little s, that means normal, right? And then they have the Y sex chromosomes. So 0 out of 2 is equal to 0% for the sons having Squidward's disease. Okay, daughters are on this side. Okay, the daughters, the only possible genotype they could have is 2 out of 2. So that means even one big S, X big S, would result in Squidward's disease. So both of these genotypes lead to Squidward's disease. So 100% chance for daughters. to have 6 words. Okay. Again, this is because big S is for Squigler's disease. Little s is for normal. Okay, so both of those possibilities for the daughters, um, like they're the same. That one little big S, that one big S will cause them to have Squigler's disease. Okay. Now let's do try it for yourself part 5. So Buddy's disease is characterized as a disease that causes people to travel in counterclockwise circles for long periods of time without stopping. Buddy's disease is Y-linked and represented by the allele little b. Jasmine's father has Buddy's disease, but her mother does not. Jasmine's husband has Buddy's disease. Jasmine wants to have twin girls, but is worried that she might get Buddy's disease. What are chances her future twin girls will get Buddy's disease? Okay, so pause it and go ahead and solve it. Okay, so let's try solving it right here. Okay, so there's a lot of information here. So it's a Y-linked disease. So we know that Jasmine's father has Buddy's disease, but her mother does not. Okay, since it's a Y-linked disease, the allele is only on the Y sex chromosome. Okay, so if Jasmine's father has Buddy's disease, then he is X, Y, little b. Okay. Jasmine's mother does not. So since Jasmine's mother does not have any Y chromosomes, she only has 2 X sex chromosomes because she's female. She's just X. Okay, she doesn't have any of the alleles for Buddy's disease. And then it says Jasmine's husband has Buddy's disease. So he would be X, Y, little b. Okay. We don't know Jasmine's genotype, but we can kind of figure it out by doing the Punnett square for Jasmine's father and mother. Okay, so let's say that Jasmine's mother and father, they decide to have children. So we do the Punnett square. Okay, so Jasmine is somewhere here. Okay, it is not possible for any of the daughters born to that family to have Buddy's disease because they don't have any Y chromosomes. Okay, the Y chromosomes from Jasmine's father only goes to the sons. So in this case, this side right here. So Jasmine, since Jasmine's a female, has 0% chance of getting Buddy's disease from her father because Buddy's disease is on the Y sex chromosome, and she doesn't get a Y sex chromosome from her dad. Okay, she gets the X sex chromosome from her dad and an X from her mom. So Jasmine has 0% chance of having Buddy's disease. So her genotype is XX. Okay, and if we cross Jasmine and her husband, okay, because now we know her husband's genotype and we also know Jasmine's genotype. And we do the Punnett square. What are chances her future twin girls will get Buddy's disease? 0%. Because again, the daughters cannot get Buddy's disease because they don't get any of the Y sex chromosomes. Okay. However, if she were to have sons, they would all get Buddy's disease. All right. So now we're going to move on to pedigree charts. Okay. So here, this is a pedigree right here. And then So let's talk about like determining like all the stuff on the pedigree. Okay. So the squares right here are males, and the circles represent females. Okay. The Roman numeral right here, where it says 1, 2, 3, 4, like that, they represent the generations. Okay, so the generation one right here, that's the oldest generation. Okay, the second generation is the second oldest, third generation, third oldest, and then the fourth generation, the lowest one, or like the highest in number, is the youngest in terms of age. Okay, so I guess you could say like these are the great grandparents, the grandparents, number two, second generation is the grandparents, third generation are the parents, and then like the fourth generation are the are the great grandchildren or something like that. Or I should say great grand are the children. Yeah. Okay. Oh, the lines in between. So right here, there's like a horizontal line between the square and the circle. Okay, they represent a marriage. Okay, and the line going down from that horizontal line, that represents children between these two. So the one right here next to the square and the two next to the circle represent the individuals in that generation. So in generation one, there's individual one, individual two. Okay, so these two have two children. So if you look at generation two, there's this circle and this circle right here. Those are two daughters. Okay, so individual one and two in generation one has two daughters. They're in generation two. Okay, um, the reason why there's a line that goes on top of them and then connects to the people from generation one, that shows that they are related, meaning that generation two circles, because they have a line on top of them going up to generation one, they are the offspring of generation one. Okay. Okay, so let's go over some of these things. Okay, so number one, in a pedigree, a square represents a male. If it is darkened, he has hemophilia. Okay, if he is clear, then he has normal blood clotting. How many males are there? So in this pedigree chart, there's 8. There are 8 males because I counted eight squares. Okay, how many of the males have hemophilia? So um, in this case on the pedigree, if they're darkened, that means they have hemophilia. So 1, 2, 3. So have three have hemophilia. Okay. So a circle represents female. If it is darkened, she has hemophilia. If it's clear or open, then she's normal. So how many females are there? We count the circles. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8. So 8. And then how many females have hemophilia? 1, 2. Okay. A marriage is indicated by a horizontal line connecting a square to a circle, or circle to a square. How many marriages are there? 1, 2, 3. There are 3 marriages. Okay. A line perpendicular to a marriage indicates offspring. The line ends in either a circle or square. The couple had only one child. However, if the line is connected to another horizontal line, then several children were produced, each indicated by the vertical line connected to the horizontal line. The firstborn child appears on the left, and the lastborn child appears on the right. How many children did the first couple have? So couple in row 1. So right here, they had two daughters. Okay. Again, individual 3 in generation 2, that person is the oldest daughter. Okay. So they had 2. How many children did third couple have? So the couple in row 3 or generation 3. Oh wow. Okay, they have 1, 2, 3, 4, 5, 6, 7. 7 children. Wow, that's a lot. Okay. And then on level 1 or generation 1, level 1 represents first generation. Level 2 represents second generation. How many generations are there? So that's 4. And then how many members are there in the fourth generation? So we already counted 7. So 1, 2, 3, 4, 5, 6, 7. That. Okay. So that's basically how we do pedigree charts and we analyze it. Okay. Now let's try a actual problem. So this pedigree chart shows the passing of color blindness. Um, what sex is most likely to be carriers of color blindness? Okay, so here's the thing. With pedigree charts, sometimes you have to kind of figure out if we're looking at sex-linked traits, if we're looking at or autosomal traits. Okay, so in this case, um, it looks like this is a sex-linked trait. Okay, because it's talking about, the question says which sex is most likely to be carriers of color blindness. So that means it's referring to, the trait being on the sex chromosomes. Okay, so this is a sex-linked pedigree chart. Okay, so right here, it looks like which sex is most likely to be carriers of color blindness. Okay, to be a carrier um, for a like trait or disease. Okay, that means that the what do you call it? The alleles, um, the trait color blindness has to be a recessive allele, and the dominant allele is the normal allele. Okay, so for in this case, right? Let's say that color blindness will be represented by the little c allele, right? That's color blindness. Big C is normal. Okay, so how do we know if color blindness is on the X chromosome or the Y chromosome? Okay, so if color blindness was on the Y chromosome, okay, only the sons will be affected. But you can see right here, there are um, there is one circle right here, one daughter that has color blindness. So it would be impossible for it to be a Y-linked trait. Okay, color blindness has to be an X-linked trait. Okay, so individuals that are half shaded, like let's say this person right here, right? They indicate carriers, meaning that they're not colorblind, but they have one recessive allele for color blindness. Okay, so what that means is they are X big C, X little c. Okay, so since big C is dominant over the little c, that person is not colorblind, they're normal, but then they have a recessive allele that they could possibly pass on to their sons or daughters. Okay, that's what it means to be a carrier. You carry that certain trait that we're talking about, so in this case, colorblindness, but you don't actually have it. Okay, because that trait is a recessive trait, and your dominant allele is hiding that. Okay, and then you're normal. Okay, so in this case, which sex is most likely to be carriers of color blindness? If you look at this pedigree, um, it's all like the circles that are half shaded. There are no half shaded, squares. Okay, for sex linked pedigrees, it is impossible for males to be carriers. Okay, for sex linked, not for the autosomal ones. Okay, because males only have one X chromosome and they only have one Y chromosome, so it's impossible for them to be carriers. Okay, so the answer for this would be female. Why does individual in generation 4, or individual 7 in generation 4, a female have color blindness? Okay, so this is individual 1, 2, 3, 4, 5, 6, 7, and this is 8, right? So we're talking about this person here. Oh, wow, okay, that didn't turn out well. Okay, this person there, okay? So why does individual 7 in generation 4 have color blindness? It's because right here, her parents, okay? The genotype for the mom of individual 7 in generation 4, she is X big C, right? And he's X little c. The male, on the other hand, her father is X little c y. Okay, so if you did the possible Punnett square, individual 7 is basically this one right there, X little c, X little c. So that's basically the reason why she's colorblind, because her dad is colorblind and her mom is a carrier of colorblindness, and her mom gave her the X little c um, sex chromosome, and her dad gave her the X little c chromosome, sex chromosome. So that's why she ends up with X little c, sex chromosomes, and colorblind. Why do all the daughters in generation 2 carry the colorblind gene? So generation 2 is right here. This is because right here, the square right here, that's the father, right? The father is X little c y. Okay. The mother, she is clear and she is not half shaded, so that means she's not a carrier and she doesn't have hemophilia. So she is X big C, X big C. Okay. The reason why all the daughters in generation 2 are carriers is because they can only receive the X little c from their dad. Okay. The dad has 2 sex chromosomes, right? He could give the X with the little c allele or a Y chromosome. Okay. If the dad gives a Y chromosome, then you would have a son, because the mothers, they can only give X sex chromosomes and whatever's on that X sex chromosome. But for the fathers, they could give an X or a Y. Okay, so fathers in this case actually determine the genders of babies. Okay, because women, their eggs only contain X sex chromosomes. Fathers, their sperm can either have an X sex chromosome or a Y sex chromosome. And then list 2 generation 4 colorblind males. Okay, so that would be this one, individual 1 and individual 5. Okay. And now let's move on to our next set of problems. Okay. So, this is a pedigree, not much information shown. Okay. So, questions asking, is this trait dominant or recessive? Explain your answer. Okay. So, here's the thing. You get a pedigree. You get that much information. So, you need to determine, is this pedigree, the trait that we're looking at, is it on an autosomal chromosome? Is it like an autosomal, we have to do autosomal Punnett square and like stuff like that, or is it a sex linked? Okay, meaning that it's on the X or Y chromosomes. In this case, okay, what do you call it? Since it looks like very few individuals have this particular disease / trait, right? It is most likely, an autosomal recessive trait, just because there's so many individuals here, and both the males and females seem to get it. Like, is most likely a autosomal recessive trait. Okay, if a lot of the males and females end up with this disease, then it would be a most likely autosomal dominant. If like it was one or the other gender that was affected a lot more than the other gender, like let's say it was mostly males that are affected versus like females, then probably that's a sex-linked trait, like pedigree. If it's mostly females that are affected and very few males, then again, sex most likely a sex-linked pedigree, okay, or trait. Um, so because both males and females are affected, but not in large numbers, this is most likely a autosomal recessive trait. And what gave you the essential information to decide that individuals 3 and 4 in generation 2 were heterozygous? Okay, so you gotta look at the parents, right? So this one and that one. Okay, so if individual 1 is colored, that means they have to have 2 recessive alleles. Okay, because we've already said that this is an autosomal recessive trait, right? So let's use any letter. Okay, so in this case, I like using the letter H, right? So H, big H is normal. Little h is whatever disease, right? Whatever disease that we're talking about here. So that means individual 1, the father right here, has to be little h, right? The mother, um, the mother, she can be 2 possible genotypes. Okay, so the mother can be X, sorry, big H, or she could be little h. Oh, sorry, big H, little h. My bad. So the mother can be individual 2, can be big H, or big H, little h. Okay, we don't know. Okay, we don't know, but for the most part, it's not going to matter. Okay, because if we do the Punnett square, right, and let's say she's big H, right? Or okay, those are like the possibilities. Basically, for this case right here, if the mother is big H, there's none of her children will have the disease. Okay, if the mother is heterozygous, she has big H, little h, then 50% of her children will have the disease, 50% will not have the disease. Okay, so what do you call it? If you look at the 3 children, none of them have the disease. Okay, the odds are, 50% of the chance they'll have a child with the disease. Okay, so most likely the woman, individual 2 in generation 1, is big H, big H. So what that means is, in generation 2, the children, individual 1, 2, and 3, are most likely, the big H, uh, little h genotypes. Okay, so they're heterozygous. So that's basically how I figured that out. Okay, if the mother, individual 2 in generation 1 right here, if she was X big H, X little h again, there's a 50% chance her children would have the disease, right? And she had 3 children, and since 1 or 2 of them don't have the disease, most likely that's not her genotype. And that's it, guys.